Hello everyone. In this video, I would like to show how we can use SWATCUP to design a filter strip. In the last video, I showed how to do risk analysis using an example of terracing. You can do the same thing for filter strip here. However, in this video, I would like to show how to use SWATCUP to design a filter strip to minimize sediment, total nitrogen, and total phosphorus transport out of the watershed under uncertainty of the parameters. Now, often people ask me, so what do these parameter ranges mean? So what can I do with them? Now I calibrated the model and I have these calibrated parameter ranges. So the answer is that the calibrated parameter ranges are acceptable ranges of parameter values given the uncertainties in your model. So because your model is uncertain, therefore when you calibrate, your parameters are going to be also uncertain. So your model uncertainty comes from soil, land use, climate, management information, simplification of the model, and so on. So because of these uncertainties, which are inherent in the watershed model, we are going to have uncertainties in the calibrated parameters. So now how you can use these ranges is you have to propagate them through your model to whatever that you want to do. For example, land use change analysis, climate change analysis, various implementation of BMPs, and so on and so forth. Anything that you want to do with your model, you have to propagate these ranges. And you propagate them, of course, by sampling. And in SWATCUP, we do that by sampling through Latin hypercube. Now, for design purposes, such as the example I'm going to give you now, it is best to use parameter ranges that are calibrated. Because in previous examples, I said there are times that you can use uncalibrated parameter ranges that you obtain from literature and so on. But in this example, when you want to design a parameter, the best is to have parameters that are calibrated and also calibrated using the behavioral objective function. Because in the behavioral objective function, when you obtain your parameters, all combinations of your parameters yield good results like NiSAT larger than 0.7 or whatever that you set for the threshold. Whereas if you use a single objective function, you may have some bad simulations in there also. So the advantage of behavioral objective function really comes to light here. Different types of objective functions, I described them before. They are in video 1, Introduction to Calibration and Uncertainty, and also I think in video 5.5, Calibration of Watershed in the Danube Basin. There I talk about the differences between various objective functions. However, having said that, if calibrated parameters are not available, then the next best option is still to use a reasonable set of parameters for your watershed and to use that as a first estimation or as an initial estimate of the parameter you are going to design. Now, filter strips, as you know, are vegetated sections of land designed to receive runoff by overland flow, and their function is to mitigate transport of sediment, nitrogen, phosphorus, and so on from the field into the river or into the next field. To design these, you have an option in SWAT, in one of the BMPs. It is the management option number 4. And these are the parameters that are provided in SWAT. So the parameters are expressed in the .ops files. So what you need here is month, day, and year when the option becomes available, and then the number of the management, and then the flag, which should be set to 1. So you have to remember the flag is here, so the dates are here. 4 is the number of the operation, and 1 is the flag. And then you have 3 other parameters, and these are mostly, they define the structure and the topography and the geometry of the watershed, I think. So I didn't find them to be parameters for calibration. So in this example, I used the default values that are given by SWAT, which is 40 for this parameter, 0.5 for the second parameter, and 0 for the third parameter. So I took these, but I don't see any reason if you want to also treat this as uncertain and give them a range. I think that would also be possible. Also, although I would be very careful because they have to do with the geometry and slope and all of that of the watershed, and maybe they could be even calculated for a watershed. Now, after you set these parameters, then in the management file, that's the only parameters that you can actually design that you have to choose. That would be the width of the filter strip, and this is given in the management file. So the objective is to design the width of a filter strip so that transport of sediment and total nitrogen and total phosphorus from the outlet of the watershed is minimized. I will show how this is done by going to the program and doing the whole thing from the beginning. Okay, now let me show you how you do this in SWATCUP. Here I'm using SWATCUP-premium. So what I have here, we start with the parameter information file. I have here calibrated parameters for flow. Then I have calibrated parameters for nitrogen. Then I calibrated the parameters for sediment, and finally for phosphorus. So if you want to calibrate for all these, this is the order that you should calibrate your model. At the end, I have our design parameter, which is the width of the filter. And there are various numbers are given for this in the literature. I took some average 10 to 20 meter filter width. So we have a total of 30 parameters, and I'm going to make 800 simulations. So for that, I'm going to start a no observation simulation. And as I've shown you before, for no observation, you just have to fix the input here. And I'm extracting from the reach file. So in the reach definition file, I'm going to extract sediment, which is column number 11, total nitrogen, column number 48, and total phosphorus, which is column number 49. And then the rest is the same as before. We have 54 subbasins, and subbasin number 26 is the outlet of the watershed. And I have 3 lines here for the 3 variables that we have here. And we are simulating from 1973 to 2006. So this is what you have to do here. And then if you go to the, then you need to go to the engine of the program, which is the executable files, and to extract batch file. And here, the only thing we have to extract is extract no observation from reach. So that's what you check, and that's really all you have to do. Then you save everything, you close everything, and I'm going to use the parallel processing. So I will make 800 simulations. Pre-processing and start the simulation. All right, the simulation is finished. The next step is to run the post-processing for no observation. But before that, let me check here that this SPE no observed post-processing, make sure that the only thing we are running is 95 PPU of no observed for the reach, which is the only thing which is checked here. So, and that is okay. Then we do the post-processing. All right, then I can save this, of course, iteration number 1. So I can look at the output, but this is the no observed output, but this is not much use. It's just to look at. This is the sediment for no observation case. This is the total nitrogen and total phosphorus. But what we want to do is go to the project, open the project here, and then in the out, SPE out, sorry, don't need the out, I need to go to the echo file. Our file output that we need is printed to the echo file, the echo of 95 PPU no observed for reach. And in this file, what you have here is our simulation numbers and the parameters, all the parameters here. And at the end, we have 3 extra columns here that give us the 3 variables that we want to simulate. That is the nitrogen, phosphorus, and sediment. So what I have to do is to bring this into an Excel file. So I'm just going to copy all the 800 simulations up to here. Copy this. Open an Excel sheet. And paste it here. And let me go to data, text to column, delimited, space. All right. So I now have all of my parameters as well as the 3 output for my 3 variables. So this would be the first one is sediment, followed by total nitrogen and total phosphorus. So this is the 3 columns that I need. Let me highlight this. So this is my filter strip, the meters, the width of the filter strip, and the resulting sediment, nitrogen, and phosphorus. So what I can do is to isolate these, to bring these 3 columns so I don't have to carry the whole thing. I bring this into a new sheet. Now here I sort on the filter strip width. So expand, yes. And then I format this field so that it only gives me just the actual number. I don't need the small digits. So here is what happens when the filter is 10 meter, right? And then as you go down, when it's 11 meter, sediment, nitrogen, phosphorus, all the way when it's 20 meters, right? So I would like to determine which one of these from 10 to 20 is the best. It minimizes the output of sediment, nitrogen, and phosphorus. So what I do is I average for the 10 meter, I averaged my simulations. That's equal to average of the sediment column. And then I can copy this here. So this is the average when it's 10 meters. The filter is 10 meters. I can do the same thing when it's 11 meter, right? When it's 11 meters, I can equal to average of the 11 meter and copy this into for the nitrogen and phosphorus. Now I do this for every one of these for different meters. Now you can write a little program in, I don't know, whatever, in C or in Fortran or in Python or whatever that you're used to do this. It's a very simple 2-line or 3-line programs. But I didn't write this because the condition can be so different. You cannot write one fixed program to do everything. So you need to do that. Either do it manually, like I showed here in Excel, or just write a little program to average these values for different width of the filter. Okay, so once I calculated the average for all the widths. I copied these 3 average columns here. Simply copy this and paste it in a new sheet as special paste as values. And then what I do is just the filter for you filter for blank, and I get my averages. I copy these. I go to a new sheet and again paste special as values. Okay, so now what I have here, let me copy these over here. So here is the width, right? Here was the width. Here is sediment. Here is total nitrogen. Here is total phosphorus. So the width is 10 meters, 11 meters, until 20 meters. Until 20 meters. So this is what I have. Now, what I want to find is to find the meter that makes these, that minimizes these, right? So let me here calculate the minimum equal to, let's see where that minimum is, equal to minimum of sediment and minimum of nitrogen and phosphorus similarly. So 65, that is here, right? 39, that is here, it's the minimum. And 100, it's here. So if you make, I made 800 simulations, right? If you make like 200 simulations, you may get these at different places. This maybe minimum is here, maybe this minimum is here, a minimum is here at different widths. But if you make a large number of simulations, like here I did 800, if you make 800 or 1,000 or more simulations, then you will get, as I tried, usually you get all of these lining up for the same width. So the same width should minimize all these 3. So it seems like 17 meters is the minimum width that we are looking for. So the design width of my filter strip in this example would be 17 meter, and that would minimize the output of sediment, total nitrogen, and total phosphorus. So it's as easy as that. If you have a calibrated model or even a non-calibrated model with reasonable parameter ranges, then you can use those parameter ranges, and as I showed here, to find what should be the best design width. Not in this case, we have the width of the filter strip, but in other cases, you may have other design parameters. So for these design parameters, you can obtain what would be the optimum parameter value for any other case, as I have shown here. So I hope that this can help you to do some extra analysis and find what is the best width, in this case of filter strip for your situation. Thank you for watching.